K nearest neighbours is really the platonic ideal of a non-parametric model. The underlying assumption is that the best estimate that we can make of the data distribution is the data itself. The only strong assumption made is that the training data is like the test data. As mentioned in week 1, that's really the weakest assumption that we can make in order for learning to be possible at all. If the training data is not like the test data, then we're basically stuffed. Training for K nearest neighbours, as mentioned in the introduction, consists entirely of just memorising the training set. There is no attempt to summarise it, there is no attempt to distill any features of it or discover anything about its shape. In fact, there is no attempt to model it. Arguably, K nearest neighbours isn't a model at all, it's just an algorithm. Prediction for K nearest neighbours consists of taking a new data sample and comparing it to all of the samples in the training set, finding some number that it is most like, and then using those to predict the output value for that piece of data. Obviously, this raises the question of what it means for one sample to be like another sample, and so we need some metric of similarity or equivalently of distance. As well as a similarity metric, we also need some kind of policy for breaking ties. The use of a distance or similarity metric means that we might lose value in higher dimensions where these things become less reliable, and we might also be sensitive to disparities in scale or amounts of noise on different dimensions. The hyperparameter K is used to determine how many of the most similar data samples from the training set we use to contribute to our prediction. As this number increases, we average or take a vote over a larger number of contenders. The consequence of this is that increasing K tends to smooth out some of the wiggliness in our decision boundaries, but it may also lose some local information. If you imagine increasing K all the way up to the size of the training set, so K equals N, then the nearest neighbours algorithm reduces to just a winner-takes-all or a global average. Obviously, in that case, you lose all local structure completely. In general, increasing K reduces the variance of the model because it reduces the sensitivity to individual single near neighbours. So let's look at a couple of examples. Here we've got a single nearest neighbour for this data set and also 15 nearest neighbours, and you can see that in the latter case the boundary is much smoother and much more coherent, and there are a lot fewer of the little islands around individual samples that occur with just a single nearest neighbour. In this second example, there are 3 classes in the data. Using K equals 1, you still get very wiggly boundaries. Using K equals 3, the boundaries are arguably a little bit more sophisticated and nuanced, but with K equals 3 and 3 classes, there's plenty of scope for ties, as you can see in the grey areas. This is why a tie-break policy becomes important. K nearest neighbours is one of the algorithms that you'll implement in the lab exercises this week, so you'll see further examples when you do that. K nearest neighbours is able to learn very complex decision boundaries or also regression landscapes. It's easy to understand and to implement. It has this hyperparameter K, which you have to choose somehow or tune, and the model can tend to overfit significantly or also underfit depending on the value of K. One issue with K nearest neighbours is that it can be hard to interpret in any kind of explanatory fashion. If the data samples happen to cluster nicely into discrete regions, then that may be interpretable. But if the data is quite patchy and there are lots of islands, then the whole thing might not make very much sense. It can be vulnerable to differences in scaling and noise and importance of the different feature dimensions. Some of this can be combated by pre-processing. However, by far the biggest drawback for K nearest neighbours is that it can be enormously slow to evaluate. For each test sample, you have to compare it to all of the samples in your training set. If your training set is large, this can take a long time. There are a number of ways in which this last problem can be mitigated. In particular, you can apply some data reduction techniques. So very often, if the data is reasonably well clustered, then lots of the neighbours within any particular neighbourhood don't really matter because there are lots of other neighbours of the same class or a very similar value nearby that will catch any data samples in that region. If you can process your data set to detect all of the ones that don't really contribute anything and throw them out, that will make evaluation much quicker. Another related approach is to apply dimensionality reduction or feature selection approaches. So if you have redundant features, remove them, that will speed up your comparison process. If you have a large number of dimensions but can compress those into a smaller number, again, that will speed up the evaluation. We'll talk about dimensionality reduction properly in a few weeks' time. Another approach that you can apply, which may improve the predictive capacity of a K-nearest neighbours model, is to apply some kind of weighting to the predictions from all of the neighbours, depending on how close they are. So neighbours that are very close contribute more, neighbours that are a bit further away, although still within the neighbourhood, contribute a bit less. This can also deal with the problem of breaking ties. In general, nearest neighbours is not that widely used, but it is a very good baseline for seeing how things behave.